Hey, hello and welcome to the next episode of 3D in 30. Today we're going to be talking about putting the Velo in material development. We're going to look at Velo 3D's material qualification roadmap. So this is how Velo 3D releases alloys to the world. If you're new to 3D in 30, this is our live format for LinkedIn and YouTube. We are holding this about every 2 weeks, and we have an amazing schedule for the next couple of months. So make sure you follow us on LinkedIn to get the latest schedule and the latest topics. You don't want to miss out on what's coming down the pipeline. You don't want to miss out on the session today. Today's going to be pretty awesome as well. So Velo 3D has a unique approach to material development. Our intent is to have every printer in the fleet basically recreate the same material. And so this is something that an engineer could use for design allowables. That's kind of the conversation or the language that people use. And basically what that means is that they know the material strength of an Inconel 718, for example. The Inconel 718, the Velo 3D prints on one printer is the same across the entire fleet of printers. And this may sound trivial, but it's actually fairly unique in the metal 3D printing industry. And this may be the first time that an OEM supplier has done this at the fleet level. And so that's what we're going to talk about today. However, we also provide solutions to a number of different industries, and all of these industries have a different requirement. So we have two things going on. We have their need for standardization, but also the need for some customization. So how does Velo 3D balance that? So today we're welcoming Dr. Robin Stamp, PhD, Director of Solutions Engineering. I'll bring him onto the show. And we're going to talk about this approach to materials development that allows Velo 3D's customers to enjoy standardization, but also flexibility for their solutions. So as a reminder, this is a live show. We want to hear from you. When you do submit questions at any time, give us about a minute or two to see the question. It does take some time to transfer through, and we'll try and answer it live. Also, keep in mind that this is about a 30-minute show. So if you do have questions, don't wait till we're 28 minutes into this because we may not be able to get to your question. Go ahead and ask your questions early. So Robin, let's hear from you. Tell us about your background.
Yeah, so good afternoon, Mike. My name is Robin Stamp. I'm a Director of Solutions Engineering at Velo. My current role is really focused on is generating material property data for the different parameter sets and materials that we run through the Velo systems. How I got to this role is, so prior to working at Velo, I was working with SpaceX, standing up some of the XE production equipment. And then before that, I spent most of my career in laser powder bed diffusion for medical devices. So developing processes and validating processes for Ti-6 for alloys and similar for implantable devices. So just as part of that, a lot of the work I've been doing is really focused on mass production, serial production of product through laser powder bed diffusion. It's kind of working out how to do that qualification and working out how to make, as you said, as alluded to, Mike, kind of make the outputs of every machine identical and to be able to verify that through your process controls. That's been a great experience both with Stryker and at SpaceX. And then, so I spent most of my career being an end user, and now working at Velo, this is my opportunity to really kind of help reduce those barriers of implementation for a lot wider audience rather than the kind of the end users that I was currently working for.
Yeah, and you mentioned the industries. I mean, you got medical and you've got rockets, and if something's not going right with the materials, if the materials don't perform as required, you've got significant consequences. So it sounds like there's a lot of pressure to make sure these materials do what they're supposed to do.
Yeah, and there's a lot of, so I guess one of the big barriers you have when you're starting out with a product that you're going to use 3D printing for is there's a lot of risks and uncertainties around what that product is and what that material is. And that's kind of really what we're trying to get at Velo from the perspective of, if you're a designer for a new product, you want to switch to additive, you don't necessarily, if you haven't minimal experience and no real support from the traditional support from the vendors, you've got a big kind of risk timeline there for how long does it take me to get to the process where my material is going to meet what it's going to be? Is my material going to actually be what I want it to be? And then how do I put a kind of qualification and validation process in place to make sure that part number 1 is the same as part number 1,000 that I'm making? So it's kind of, People have been doing it. A lot of people, so some organizations, but most of it happens within that organization and it stays effective intellectual property. So from Velo, we're really trying to target that we as the equipment manufacturer, we can provide and support our customers in doing that to take away a lot of that risk, a lot of material risk, and timeline risk, and technology risk, so that you should be able to get to market faster for new product applications using laser powder bed fusion.
So we actually have our first question. Somebody's taken us up already. Mo, thank you for the question. This is an interesting one. Since we're still kind of in the bio and talking about your background, what was it about Velo 3D that made you leave one of the most established companies in the world, SpaceX, and I don't know that we were a startup at the time, but he uses the word startup.
So yeah, you're right. So SpaceX is a phenomenal experience, and I think anybody who gets the opportunity to work there, it's incredible. And they are pioneers in their kind of implementation of laser powder bed fusion for kind of large printed components for their systems. It was actually working at SpaceX where I started working on the Velo technology. Although that wasn't the first time I'd seen Velo. So Velo, I guess, I don't know, Mike, you probably know better than me, but Velo's been around for kind of first product maybe 4 or 5 years or so from the kind of the first sapphire printers. And what you saw with Velo was a real innovation in parameter development and how you configure a system, a laser for melting product. Traditional manufacturers, and they stayed quite the same for quite a long time. It's quite a simple system where you have a contour, you have an infill, and then you do a slice by slice by slice. Velo was really, when they started out, really were the first significant innovators in how you can do that better and how you can start to overcome some of the limitations of that technique, particularly around kind of surface finish. And if you're familiar with powder bed fusion devices, typically your surface finish here is a little bit different to the surface finish there, to a little bit of the surface finish there. And that's really where Velo started to pioneer new strategies and innovative process strategies that allowed us to do something different. And for me, that was the real hook for Velo, kind of understanding, the technology that I've been using for, I guess, best part of 20 years had been pretty stable for those years, but albeit some kind of laser power developments and things like that. But really for the kind of the novelty and the innovation for the process design, that's where I was kind of really curious for, and especially as somebody who's been a process developer and a process tweaker for 15, 20 years, to see someone doing it so much better than what I've been doing it was just kind of like it was a great experience. It's great to see people enhancing and progressing the state of the art in the way that Velo did.
Yeah, it's one of our marquee parts is kind of this shrouded impeller idea, and this is sort of where we made a big entry into the market, was being able to do these low angle surfaces like this without any what we call support material or anchors to hold the part down to prevent warping. So it's kind of a good example there.
And just to say that, so kind of when we first started talking to Velo back when I was working in the med device world, it was clear that they were trying to do different things for additive manufacturing equipment. So serial production, kind of like the machine that produces the same output time and time again, was one of them. And the other one really was kind of like really embedding the software developers and the kind of the software that designs the parts and generates the slice data is embedded in as fundamental parts of the business, as well as the hardware. Whereas traditionally, maybe you got hardware vendors who had a few guys doing software, or maybe they outsourced it. Velo was fully vertically integrated in that, and that's what I think allows you to do that. So you can have the process development guys have great ideas about how to do something better, but they're immediately partnered with the software guys who can actually bring that to reality and quickly, and to be able to develop on a test platform.
So let's dive in here and actually walk through, how do you develop a new material, give people some understanding of that. Dave, we'll get to your question once we cover that section.
How do you develop new material? So, all right, so I'll step back. So traditionally, like developing a new material was always kind of like a bit of an art form as well as a science. So there's a certain amount of point the laser at the material and kind of like see what the material properties were. And there's obviously bounds within that. With Velo, so that kind of works for kind of 1 or 2 materials. And when you look at kind of where you get to with with Velo, both of the process complexity and the number of materials we support, that's when it starts to get, you can see why that's what one of the things that drives it to the next level of how do you make this into a process that can be developed and rolled out rapidly across multiple materials as and when those requirements come in from different customers. So within Velo, there's a very structured methodology around and very kind of data-driven methodology around how to generate the material from first principles, tailor it in for each of the different kind of sub-processes that we use within the part, and then kind of release that as a process set. And that's kind of all, to be honest, again, as someone who is previously an end user and probably considers myself an end user, that's the bit of the kind of the mind-blowing bit for me around kind of how you put controls around that process development process so that you can develop this very complicated and very sophisticated process strategy for a new material. Sometimes I guess within maybe 3 months would be a good timeline for saying kind of from start to scratch to get to the point where you're releasing that process set. And again, for someone who's in the middle ages of their career, it's great to see kind of 20, 30 something process engineers doing things almost an order of magnitude better than what I did previously in kind of the start of my career. So that's the core, some of the real complexity I think at Velo, which allows you to kind of take this principle, this recipe set, and apply it to, I don't know, I think we've got 13 materials or something kind of released currently on our printers, and then there's always new ones coming through in development.
Yeah, that's our list right now. 13. But we need another one if you think 13 is an unlucky number. We need to develop some more. So we have copper. So this is one of our more popular alloys, GR-Cop42, NASA-derived alloy. And this one was not without its challenges. Can you kind of give us a little bit of color, maybe an example of that material development looking at the copper alloy?
Yeah. So copper's one of those ones which is a relatively recent alloy to come across in laser-powered bed fusion. It's traditionally, I think, been very difficult to do because of the kind of getting the right alloy composition to allow it to be easily welded, and also kind of how to manage that energy input, because it's very, very reflective and both reflective and conductive. So it's very difficult to contain that energy into that very small focus spot that you need to produce your weld. So I think that the ability to go from kind of the basic recipe for copper to making it work to a very sophisticated product like that is an example again about how we kind of effectively encode that process strategy into all of our procedures to allow us to get to that endpoint. And I think it's also enabled by our partners who develop different alloy chemistries that allow it to allow that material to be better formed within a laser-powered bed fusion system.
Yeah, you mentioned reflective, conductive. It's also in this case has a very high melt temperature. So you have to you have to meet that threshold of energy in a very short amount of time with all that reflectivity going on.
Yeah, and that's kind of like there's certain kind of like core elements of something like a Velo system like it. So they're all kilowatt lasers, the variable focus. So on those systems you can go anywhere from kind of 100 watts to 1,000 watts at various and configure that spot size, so change the energy density as you're going. So that kind of flexibility and kind of platform capability allows you that freedom to move from different alloy to alloy and solve those problems.
Yeah, and now we've got two. We've got two coppers, GR-Cop42 that we already mentioned, kind of walked through, and now C18150 for launcher. So we're stacking up the coppers now. We have as many coppers as we have Inconels.
Yeah,
moving forward with that. That's pretty awesome. So now we have a couple questions. So let me jump over here to Dave's questions. Dave asked, so OEM requirements vary greatly, and what percentage of the requirements tend to overlap or be the same? And then he has a follow-on, and we list the number of alloys here, 13 alloys. That's not all of them. There are some proprietary alloys that we're developing for customers that we don't put on the list. So, how does that layer of need also kind of shadow or put its mark on your development as well?
Yeah, it's a good point. So you're right. So there are a number of different kind of variations to the alloy manufacturing process and performance that we come across. So in some ways we do a lot of the work I'd say all of the work we do at Velo is very much kind of applied based on customer requirements. So we generally start with a product and material requirement, and then we work from there. One of the things we can do, so that, that's the traditional approach, and maybe you replicate that internal customers, heat treatment, and that data stays with them and things. One of the things you can do from the machine manufacturer, and it's kind of really where my job comes, is we can also kind of do some of that work as well. So we can do, like, heat treatment is always key. Like the printed part is just one aspect of the manufacturing process. Heat treatment is usually pivotal in the final material properties for pretty much every alloy that we manufacture. And if you look at something like Ti-64, you could probably go to 10 different customers and find 8 different heat treatment recipes there. So from our perspective, what we can do then is start to kind of do those internal studies and understanding the impacts of the different permutations, and then which ones are best suited for our end applications. So we very much focus on aerospace and aviation at the moment. So part of one of the approaches we're doing is we collaborate with NASA on our alloy development, so that we get to a point where we can put our best foot forward from both the laser process strategy and the heat treatment strategy that gives you the alloy material properties, both kind of microstructural and mechanical, that you need for end service. So that's where we can start to help those people who are newer to the market, who maybe don't have that legacy product that they're trying to manufacture, or that legacy process they're trying to replicate, where we can say that if you're prepared to take this manufacturing process, this process validation that we prepared, and these material properties, this will be your material properties, and it saves you, I don't know, 2-3 years worth of internal R&D development if you want to do it that way. So that's really how you get to reduce that barrier of entry for new products, so by kind of helping people standardize on the process recipes that we can apply on a Velo system and the heat treatment to give these material properties.
Yeah, now I know CP1 was one we launched right before Rapid. One of the things with CP1, it kind of, for the first time that I've seen it publicly, is that we're offering different layer thickness for this process. So you've got a 50 micron, which is our standard layer thickness. You see that with all the alloys, but now with CP1, we're offering 100 micron layer thickness. And then in some of the alloys now we're looking at different core powers. So that material properties element that you're talking about being not just, it's Inconel 718, now it's Inconel 718, and there are different choices, I guess, or different selections you can make based on your industry. So, if you need something that's very, very high end, like aerospace, that's there. But if you need faster printing, then like that's there too. So it's pretty interesting what's going on now.
Yeah, it's very interesting on kind of the different customer requirements you get. So in some levels, we have customers who are making products on legacy systems, 3D printed systems, and want to effectively replicate those material properties, in which case throughput maybe not their biggest requirement. Maybe they have a qualified material property set which they need to hit, so that's what we need to hit. So on some level, we kind of like roll back our process to those 100-200 watt type laser process parameters, and based on the customer requirements. The other side of it is, one of the big impediments still for additive for a lot of products is cost, and the key part of reducing that cost is increasing throughput of machines, and that's where we get to with most of our processes. We have kilowatt options. All our systems have multiple lasers, but it's 2 lasers for a Sapphire system, 8 lasers for an XE system. So you can really start to see, as you're depositing with a kilowatt energy with multiple lasers, that's where you really start to accelerate your throughputs. Where like if you think about some of the big aerospace products that kind of people traditionally made, that they used to take, I don't know, it wouldn't be unheard of to take 14 days or something crazy on a single laser system, and now with an 8 laser system, that it's like a day and a half, 2 days print with optimizations and laser paths. So you can really start to have a significant impact in the commercial viability of our products, with kind of throughput increases that allows you to actually apply this technology into serial production. Yeah,
just showing kind of the choices here. You've got Sapphire. By 1MZ, we mean a meter Z height. That's basically what that refers to. And then you got the Sapphire XC, which is the larger platform, 600 millimeter diameter build plate. And that's where you're going to find these 8 lasers that Robert's referring to. It's an amazing system to watch print. Just so many lasers and so much functionality going on. And they are pretty quick turnarounds.
Yeah, I still remember the day when I first saw it for a kilowatt processing, and you used to watching that little dot dance around at 100 watt, 200 watts, and then it's the kilowatt. You're like, wow, it blows your mind. And then you're right, with the XE with 8 lasers processing simultaneously, it's proper science fiction. It's good.
Yeah. So catching up here on some of the questions, Dave kind of asks about the requirements being proprietary. Are we having good conversation? Are we having conversations with OEMs? They're pretty transparent about the requirements on what they need from the materials with us, or how do you work around that?
Yeah, so generally from a OEM, we have kind of target requirements that we will shoot for, and again, you can tailor your processes to a certain extent to kind of configure the output from your printer, and then the heat treatment is obviously a significant step. So typically, some people have a heat treatment that they're trying to replicate anyway, so that's not a variable. In some cases, there is room for the heat treatment work, so we have kind of material scientists within Velo who can support that. And we've done a significant amount of work on, I don't know, Inconel 718, Tie 64, 625. There's a lot of heat treatment optimizations you can do, which tailors the properties that you care about. So in that respect, we're fine. And then some end users will choose to keep their material properties internal and do their own qualifications. That's part of the business model. And then other times we can generate that data and make it more widely available as a kind of like a standard process set and process recipe that you can apply it from Velo.
So I have a question from John here. What are our upcoming materials, and what do you think the holy grail material would be that you like to make but continues to remain elusive? Interesting question.
I'm not sure I can talk to that one, can I? Go on, Mike. What are
you have to be vague. So I think we have mentioned, coming soon stainless. So we're working on some stainless materials. Yeah, I'm curious to see how you answer. There's one that comes to mind that we've had conversations around, but I'm trying to think of how we be vague about it. There's some new industries that we're pursuing where there are some requirements for alloy performance, and we're working directly with OEMs, and the transparency there, and that's kind of what I was referring to before, is OEMs are fairly transparent from what I've seen on what the requirements need to be. And our engineers work very closely with OEMs to develop the solutions that they need. So I've seen a lot of success with that. CP1 is a great example. We work with PWR. They were using F357. They were interested in an aluminum called Ahead CP1. It's provided by Constellium. And this was specifically for the Formula One industry, or Formula One racing. Formula One is going to allow CP1 to be used in cars racing in 2024. And this is something that PWR worked on. So they did not have that alloy installed. They worked with our engineers. Our engineers qualified it in Augsburg. That's our facility in Germany. Now we have initial parameters for that alloy for 50 micron process. We're tweaking for 100 micron process. So PWR is going to be able to print the parts they need for the 2024 season. That's just kind of an example of where this traction tends to work. And at least one that's been public. We've done this a number of times so far, but that's definitely one that was a public case study around.
Yeah. And then I guess that's the other thing we see. So there's different alloys, and I think it's fair to say that Velo has a kind of a very capable applications and business development team. So there's alloys there that they're not there that you want to see. I think they're always keen to understand those requirements and help new customers. And then the other side of what we quite often get involved in is how to take some of the cost out of the process. So you start to get to the point where the throughput of the machine is so massive that maybe the powder element becomes a more significant cost in your final product costings. So then you can start to we start to work with different powder particle sizes and reduce the cost of the raw material. And then, as Mike mentioned as well, kind of working with different layer thicknesses and things as well to start to really drive some of that cost out of the process. So that's the other side of the new alloys. And what can you do to make the biggest difference? It's not necessarily alloy, like the type of alloy, but it's kind of what kind of throughput you can get from a machine, and what kind of consistent quality can you get from a machine.
So Dave asked another question. 3 months seems aggressive for releasing a parameter set. What about chemistry and heat treatment? I actually think this is it's a fair question, and probably gets us into this idea that that 3 months gives us that initial, but then we're going to go farther. And I think this is basically what you do every day.
Yeah, exactly. It's a very good question, because you're right. 3 months effectively gets to the point where you know that you have confidence that the material coming out of your printer meets the kind of the performance criteria that you set it. So maybe that's density, surface roughness, chemistry, that kind of thing. After that, then you're really looking for kind of what's the rest of the manufacturing process step looks like, and then how do you start to put qualification in place. So that's almost like, you can imagine that first 3 months is us and Velo getting a point where we're ready to start engaging with a third party, like someone like NASA. That's when we then go through kind of some of the microstructural work. We go in parallel, we do the heat treatment work, and then at that point, thank you, Mike. So you can see we kind of split it into 3 different tiers. You have tier 1, which gets you to that point where you're making material. We then work with third parties like NASA to start to understand that the material is fit for purpose once you combine it with the rest of the manufacturing process. And only at that point, once you're satisfied that you're ready to go, do you go into something like a tier 2 characterization, which is a full material characterization. So at tier 1, maybe we have some of the critical material properties developed, but tier 2, you go into the kind of the full test matrices that's targeted by our kind of the regulatory bodies where our products might go to. So for example, maybe that's an MMPDS type submission. And you're right, in that case, for the full material characterizations, those can be like hundreds of thousands of dollars of test campaign and 6 months to 12 months worth of work. And there you go. There's another slide just playing up. So this is a typical example of what we'd be doing for something like an MMPDS print, which is for aerospace and aviation applications. So you can see, as we would then start to challenge the process and the process controls. So we have all the different material properties, but we're also making sure that we're challenging different powder lots, different printers, different heat treatments. So that's really kind of like, back to your very original point, we're demonstrating that the same output, you get the same material output using our process recipes and controls from machine A to B to C to D, and that can be in your contract manufacturing network, or it can be in inside your printing manufacturer.
Yeah, so it's kind of a schematic of that, and
yeah.
So there's a question here from Tan. He asks, when can metal AM be competitive with CNC in terms of cost and quantity, or quality, actually, not quantity? And I actually think that, I mean, obviously the answer is it depends, but I think the interesting thing is how it depends. And from what I've seen, the parts that we're engaged with tend to be 2 categories. One is the alternate manufacturing would be casting or something like that, but they need initial quantities. So smaller quantities, or they need them quickly. And maybe 5 years from now, they would switch that to casting. But right now, in order to accelerate time to market, in order to meet their needs that are small quantity, they'll look at metal additive. I think there's an alternate side of this, which is parts that are just too complex to make any other way. And that's the interesting one, because that seems to be the emerging market, where you see things like, here's the IMI valve, where you could potentially make this, but it's a nightmare to make it. It's just so much simpler to print it. So the part starts to cross over into too complex. But IMI is looking to redesign this to take full advantage of AM, which would put it into that there's no other way to make it category. And when that happens, now you've got no alternative. So no matter how many zeros are at the end of the number to get to a quantity, you've got no other way to make this. To get the full optimization available to you, it's scaling up with AM, and that's basically it. So I mean, CNC is going to have its role. And if you see this part when it's finished, it's actually, a lot of this is post-processed, and there's a lot of machining involved in it that kind of gets you to the finished part. So they work together. But that's what I've seen. Have you have other experience?
No, exactly. I think I feel like there's a place for all the different manufacturing technologies. Additive is not going to completely overtake CNC. There's always going to be the parts that you want to manufacture by CNC. It makes no sense to do it any other way. But you're right. Like the ones that really blow you away that you see our customers do are the ones where they really kind of capture some of those complexities. So maybe it's 50 different individual parts all harnessed into one printed product, which then allows you to do design optimization and that you weren't able to do before. Those are the ones that you think that's where you see those killer applications, and you see the power of the technology, both in what it can do and the speed of design iteration as well. So you get so much more design iteration and product complexity in an additive component, just because the cycle for iteration and development is so much more rapid than if you're using multiple components, all of which are fabricated together. Same in orthopedics. Like from an orthopedics point of view, if you had a finite period to develop a product, you saw so much more opportunity for product innovation in the additive products compared to the traditionally manufactured.
Yeah, so I got a question here from Michael. He's asking, how important is post-processing for us? And then I noticed we are over 30 minutes, so we'll finish on that one. We'll get your final thoughts, and then that'll probably be it for 30 minutes. But great questions from the audience today. Love this.
So the post-processing, the key one, obviously for material properties, is heat treatment. So I think we've spoken about that already. There's a lot of art, and it has a huge impact on the final material properties that you're preparing. And then after that, so you can have some surface modification techniques, and depending on the additive print you're using, sometimes you can get to, there's some surfaces that are rougher than others, which then leads you into kind of like the more importance of post-processing. I think that's I'm a bit biased, but obviously I'm working for Velo now, but that's kind of really where you start to see kind of Velo having an impact as well, because it starts to mean that you can start to build those tubes or those overhangs and things where previously you had supports in there. Now you don't necessarily need that, so that you don't have the constraints that you might have had previously around having to get access to the internal geometry to do post-processing when the surface you're making it actually doesn't need that, because we've done process optimizations to do it. So that's, I think I've forgotten what our old tagline was it can without compromise, but that's really kind of one of the key benefits to having a more sophisticated process strategy, that you can start to delete some of those manufacturing controls that you previously had to put in that meant that you had to get post-processing there and added cost and labor to your part. Now you don't necessarily have to do that if you have a process that can manufacture without those constraints.
Yeah, and you mentioned the heat treat. There's obviously mating, surfacing, and finishing, and all these kind of things. So these are metal parts. So you're going to do the standard operations you'll do with any other metal part. Imagine a casting. What would you do with a casting? You might be machining, finishing surfaces.
Yep.
There are times we would put like a wall or maybe supports on there. You machine those off in order to get your final tolerances. So that happens all the time, which is why we have this great network of contract manufacturers who are very good at this. So we tend to focus on the AM side of things and getting material properties and geometric accuracy from a printed part. Our contract manufacturing network is a network of companies that specialize in contract manufacturing. That's what they do. They're not, print it and send you a printed part. These guys will send you a finished part done with all the heat treatment, all the machining. You've got all the service finishing that you could imagine available. And they are able to do that for you if you're interested in additive parts. So if you do want to try additive and you're interested in trying the Velo 3D solution, you don't have to invest in a printer. You don't have to invest in a facility to get started. And a number of our customers, this is exactly what they do. They use the contract manufacturing network. They use the standardization approach that Robin's been talking about, getting the same material, same geometric accuracy across the board. So regardless of Velo 3D printing you, maybe a concept piece, you go to a contract manufacturing network, you get a couple parts printed throughout the year, you decide to invest in a printer, you get it installed in your facility, you're going to see the same material properties, the same geometric accuracy, and you'll have the same experience across the board. So that's a very common on-ramp for customers to do. It definitely takes some of the pain out of adopting AM, and part of the value proposition that we're proud of.
Yeah, and I'd add to that. So again, the role of my job there is to start providing the additional details you need to be able to put design allowables into your product. So you know what those material properties are, you know what impact a surface finish has to your kind of tensile or your fatigue performance. So that's where we start to add the additional value that kind of, again, takes out some of those barriers to entry that you may have had previously if you did without that having access to that data when you're looking at that first product.
Yeah, and if you're interested in learning more, We Have Liftoff is a new white paper that we published, and this talks about some of the real world experiences our customers are having in getting to orbit faster. Actually, metal parts flying in space. This will walk you through a couple of those stories and give you a lot of background. It's a great asset, and we'll provide the link in the LinkedIn chat, probably in the YouTube chat too, because it looks like a number of you are actually dialing in from YouTube. Great to see that. So we'll provide the link to this white paper, and you can get a real world example of what this is all about. So Robin, any final thoughts before we sign off?
No, it's been a pleasure being able to talk to you, and hopefully it's been entertaining hearing us waffle on for 30 minutes.
Yeah, that's awesome. Thanks for joining. Audience, you've been awesome. I love the questions. I love it when we have great interaction with the audience. So definitely thank you for that. This has been a really good show. And Robin, thanks for joining us and providing your expertise. So we'll see you next time in about 2 weeks. Make sure to check your LinkedIn for the schedule. The next one you definitely won't want to miss. You didn't want to miss this one. The next one's going to be absolutely amazing. I'm really excited about it, but I can't tell you more because you got to wait for the announcement.